in the form of a theorem. So x1, x2, xn is a continuous random vector with the joint PDF and let u from Rn to Rn, where u is u1, u2, un, and ui is equal to, so ui's are functions of x1, x2, xn.
Sir, your screen is not visible.
Screen is not visible?
No, sir.
Okay, no student is able to see the screen?
Sir, I can see the screen.
Okay, are there many students who cannot see?
Sir, we can see.
Okay, so who was not able to see?
Sir, now it is visible. I joined.
Okay, maybe there was some network problem at your end. Okay, fine.
Yes, I am.
Yeah.
It's visible now. Thanks.
Okay, okay. So suppose in place of a one-to-one function, it's a many-one function. So I am just saying that for each u, it is a k-to-one function. Okay, many-one function. So suppose that Rn can be partitioned into k disjoint sets A1, A2, AK, such that transformation G from AI into Rn is one-to-one. So we have the inverse transformation, that is say x1 is equal to say h1 IU and so on, xn is equal to hn I u, I is equal to 1 to k. So from each of ai into Rn, it is a one-to-one function. So then you have the inverse image defined for that part, and that I am calling say x1 is equal to h1 I, h2 I, hn I, etc. So that means for I is equal to 1, I will call it h11, h21, hn1, and so on. Similarly, h12, h22, hn2, and so on. Okay. And we also assume, like we have the condition for the partial derivatives of the inverses. Suppose that first order partial derivatives are continuous that is denoted by say ji, that is delta. I am in a class now, huh? H1i by del u1 and so on, del h1i by del un and so on, del hni by del u1 and so on, del hni by del un. So we consider this thing, it is non-zero in the range of the transformation. The joint PDF of U, that is U1, U2, UN, is given by FU sigma Fx. In place of x1, x2, xn, you put h1 iu, h2 iu, hn iu, and multiply by the absolute value of the Jacobian and sum from 1 to k. So you can see that this formula is the same except for the summation factor here. I will give one application here when you have a many one function. So is the statement clear? The final expression here, it is only having the summation here, which is the same as for the inner part is the same as in the case of one-to-one transformation. Only thing is that we have split into k regions such that from each region you have a one-to-one function. Is it okay?
Yes, sir.
So as an application, I will derive the distribution of the order statistics. Okay, what is order statistics? So we take observations. So let x1, x2, xn be independent and identically distributed with common CDF, say capital Fx, and PDF, say small fx. Okay, so this is continuous. They are continuous random variables. We define here x1 is equal to the minimum of x1, x2, xn, x2 to be say second minimum, of x1, x2, xn, and so on. Xn to be the maximum of x1, x2, xn. See, quite often in real life applications, the ordering, or you can say the ordered observations are considered. For example, whenever there is a test here, so we look at who is the first, who is the second. So you look at your highest CGPA in the performance of any sports or in any competition. We always look at who is the best, who is the second best, and so on. So highest to the lowest, the ranking is done. So this kind of, so in statistics, the study of order statistics is of quite importance, and a lot of statisticians, they have worked on applications of order statistics. Here I will show you how to derive the distribution of the order statistics. Okay, so basically what is xn? Xn is the largest, x1 is the smallest, so xi is the ith. Okay, so let us use the notation. So this is the ith order statistics. Okay, for I is equal to 1 to n. Is this definition clear to everyone?
Yes, sir.
Okay, so we will be interested in deriving the distributions of order statistics. What is the joint distribution? What is the distribution of the largest, for example? What is the distribution of the minimum, and so on? So let us look at some of these things here. Okay, we look at the distributions of okay. So for example, let us look at the largest. Okay, that is the probability of yn less than or equal to y. That is the probability of xn less than or equal to y. That is the largest order statistics. So I am looking at the CDF here. So this is equivalent to saying x1 is less than or equal to y, x2 is less than or equal to y, xn is less than or equal to y. Are the two probabilities equivalent? Because if each and every observation is less than or equal to y, then the maximum will also be less than or equal to y. Conversely, if the maximum is less than or equal to y, then each observation will be less than or equal to y. Is that okay? So because of the independence here, because these are all independent observations, this can be written as the product of and this is nothing but capital F of y. So you get f of y to the power n. So the cumulative distribution function of the largest can be easily derived. Now in our particular case, we have considered it to be continuous random variable, and we have also taken the probability density function. So this will be continuous and we can differentiate. So the PDF can be derived by differentiating this with respect to y. So let us write it fn y. So if you differentiate this, you get n f y to the power n minus 1 small f of y. So you can do that thing. Let us look at, say, similarly the distribution of the smallest. Okay, let us consider, say, y1, that is the smallest. So let us consider, say, f of y1, that is the probability of y1 less than or equal to y, that is same as 1 minus probability of x1 greater than y. So if the minimum is greater than y, it is equivalent to saying that each observation is greater than y. Once again, if you use the independence, then this is nothing but the product of each probability being greater than y, which is nothing but 1 minus 1 minus f of y to the power n. So you have got the CDF of the smallest also. So you can get the PDF also, the PDF of y1 n 1 minus fy to the power n minus 1 f of y. Is it okay?
Yes, sir.
Let us just look at some example here. Suppose I consider, say, let x1, x2, xn be a random sample from uniform distribution on the interval 0 to theta, okay, where theta is positive. Okay, so what is fx? That is 1 by theta, 0 less than x less than theta. So what is the CDF here? CDF, if you integrate from 0 to x, you will get x by theta. So it is 0 for x less than 0. It is x by theta for 0 less than x less than theta, and it is equal to 1 for x greater than theta. So let us look at the distribution of the maximum. Okay, we want to find out the distribution of say maximum, that is xn. Okay, so according to the formula, what do you get? The PDF will be n times f of y. So this will become y by theta to the power n minus 1 into 1 by theta, that is fy, 0 less than y less than theta, which we can write as n y to the power n minus 1 divided by theta to the power n, 0 less than y less than theta, and of course it is 0 otherwise. So you can see here that by utilizing this kind of derivation, I have directly used the CDF approach here for deriving the distribution of largest order statistics for a particular distribution. You can derive, say, for normal distribution also. Suppose I consider here, say, x1, x2, xn. Suppose this is a random sample from normal 0, 1, okay, and I am looking at the distribution of xn. So if we are taking from the standard normal distribution, what is the CDF? That is capital phi, and what is the PDF? That is small phi. So what is the probability density function of the largest? That is n times f to the power n minus 1, that is phi x, sorry, this is y, x here, so this I should write y to the power n minus 1 into fy. So I hope this is clear, this formula for deriving the distribution of the maximum. So if the random variables are independent and identically distributed, so for example, if I want to find out the distribution of the maximum or the minimum, these exercises are simple here, and one can study. So for example, I want to find out how the performance of the topper will vary. What will be the performance of Usain Bolt in say 100-meter sprint, because if he is the topper. So these are the kind of things that can be studied. What is the, how the prices of the highest valued stock will fluctuate in the stock market. Okay, so these are the questions that can be answered here. Let me take up the distribution of the minimum. Another example let us take here. Let x1, x2, xn follow exponential distribution. Okay. So suppose I take exponential lambda, and I want to find out the distribution of say minimum here. Okay. So what is the formula? So for example, what is fx and small fx here? In exponential distribution, it is e to the power minus lambda x. And what is the PDF? PDF is lambda e to the power minus lambda x. So what will be the density function of the smallest? That is n times 1 minus fx to the power n minus 1. So 1 minus e to the power minus lambda x. So that is e to the power minus lambda x to the power n minus 1 multiplied by lambda e to the power minus lambda x. So let us write down it in a little bit simplified form. It is n lambda e to the power minus n lambda x. Which is again exponential distribution. With parameter n lambda now. In place of lambda, you have n lambda. Let us look at some ordinary interpretation of this. See, in the exponential distribution, you are having lambda as the rate of arrival in the Poisson process. 1 by lambda is the mean of the expected, it is the expected arrival time for the first, okay, first occurrence. So if I am looking at the minimum, so you can see if I am looking at n observations, the minimum arrival time, that means the expected arrival time of the minimum will be 1 by n lambda. So you can see it is less because I am looking at the first one. If I am looking at general one, it is 1 by lambda, but if I am looking at the minimum, it is becoming 1 by n lambda. So is it okay? Is that clear?
Yes, sir.
Now let us look at the joint distribution of x1, x2, xn. I have derived the distribution of the largest and the smallest, which will be of course of a lot of interest. Okay, but in general we may look at the distribution of all of them. Okay, so let us consider joint distribution. Okay. What is the joint distribution of y1, y2, yn? So what is the function here? Y1 is equal to x1, y2 is equal to x2, and so on. Yn is equal to xn. So I am not writing down the definition again. X1 was minimum of x1, x2, xn. X2 was the second minimum. Xn was the largest of. Okay. So if I am considering this transformation y from Rn to Rn, okay, then it is a many one transformation. Because suppose I consider two observations, say x1, x2, then x1 can be y1, x2 can be y2, or it could be reverse. X1 can be y2, x2 could be y1, because depends upon the order of the observations. So there will be two cases. But if I have three, then there will be 6 such cases, because 6 permutations are possible. So in general, then we can say that there are n factorial permutations which can lead to the same value of y1, y2, yn. Okay, so this is n factorial to 1 transformation. Okay. So one possibility is that, okay, so let us consider the inverse images. Let me write them. For example, you can have x1 is equal to y1, x2 is equal to y2, and so on, xn is equal to yn. That means the original observations are in the same order. I can have, for example, it could be x1 is y2, x2 is y1, and remaining are same. X3 is y3 and so on, xn is equal to yn. Okay, this could be another one. You may have, say, x1 is equal to y3, x2 is equal to y2, x3 is equal to y1, and so on, xn is equal to yn. Okay, that means the first and third have interchanged the place. Like that, you can have n factorial such inverses. Okay, n factorial case could be that x1 is yn, x2 is yn minus 1, and so on, xn is equal to y1, isn't it? So there are n factorial different inverse transformations possible here. Is that okay? So now we look at the inverse, determinant of the partial derivatives. For example, what is J1? So J1 is the derivative of x1 with respect to y1, that is 1, and remaining derivatives will become 0. This one is del x2 by del y1, that is 0, del x2 by del y2, that is 1, and so on, that is 0, and so on, 0, 0, del xn by del yn, that is 1. So it is nothing but the determinant of the identity matrix, that is equal to 1. Let us look at the second one. Okay, in the second one, what will happen? In the second one, del x1 by del y1 is 0, but del x1 by del y2 is 1, and remaining are again 0. And in the second row, del x2 by del y1 has become 1, and this is 0, and so on. But thereafter, it is again identity determinant of the identity matrix. So from this one, this part to this part, it is identity. Only the first column and the second column, or you can say first row or the second row of the previous one has changed. So what would be the value of this determinant? That will become minus 1, but we have to take the absolute value. So it will again become plus 1 only. In a similar way, if you look at this one, so here again it will be one interchange, that is y3 and y1. So first and third have interchange. So this will become minus 1. So if I take the modulus value, it will be plus 1. So in each case, so this is mod of J2 is plus 1. So if you argue like this, then each of them is actually plus 1, because they are nothing but the permutations of the identity matrix and then the determinant of that. So it will be either plus 1 or minus 1. So mod value is always going to be plus 1. Is that okay? Is this understandable?
Yes, sir.
So you have to derive the joint distribution of y1, y2, yn from the joint distribution of x1, x2, xn. So let us write down the joint PDF of x1, x2, xn. That is nothing but the product of the, so f of x1 into f of x2 into f of xn, because the x1, x2, xn are independent. So here of course we are considering xi belonging to R. So the joint PDF of y1, y2, yn how it is to be obtained? It is to be obtained by substituting in each region the inverse function here. So this is f of x1 into f of x2 into f of xn. So in the first region, x1 is y1, x2 is y2, and xn is equal to yn. So it will again become the product of f of y1, f of y2, f of yn. In the second one, x1 and x2 get interchanged, but since it is a product of all the terms, it remains the product of f of y1, f of y2, f of yn. Because we are only considering the permutations of x1, x2, xn here. So it will not make any difference in whichever order I write here. Okay. In whichever order I will write, this remains the same. So this product remains the same. I is equal to 1 to n in each region. And how many such regions are there? There are n factorial such regions. So the distribution of y1, y2, yn becomes this. And what is the region? Because these are ordered observations, you will have y1 less than y2 and so on, less than yn, less than infinity. So this is the joint distribution of y1, y2, yn. Is it clear? If I want to find out the distribution of any particular one here, then I have to integrate the remaining variables over the required regions. So I am just writing down for the rth one, but I am not going to derive it here. So the PDF of the rth order statistics that is n factorial divided by r minus 1 factorial n minus r factorial f of y to the power r minus 1 minus f y to the power n minus r f of y. So this is the distribution of the rth order statistics. So this is obtained from the joint one by integrating all the remaining observations. That means I integrate y1, y2, yr r minus 1, and I also integrate yr plus 1, yr plus 2, yn. Okay, all of them I am integrating out. Just one example I will give you here. Let us consider, say, let x1, x2, xn follow uniform 0, 1. Okay. If they follow uniform 0, 1, then what is f of y? That is y for 0 less than y less than 1. Of course, it is 0 for y less than 0 and it is 1 for y greater than. Okay. If I find out the distribution of the rth order statistics from the previous formula, what I will get here? F of yr, that is n factorial divided by r minus 1 factorial n minus r factorial y to the power r minus 1, 1 minus y to the power n minus r, which is nothing but a beta distribution. Beta r n minus r plus 1 distribution. So this is one derivation of the beta distribution, and of course if I want to do simulation of beta random variables, okay, then what I have to do, I have to generate n uniform random variables and choose the rth order statistics from there. So I will get a beta distribution there. So this is this gives us a one algorithm for deriving the beta distribution. Is that okay? So is this exercise clear to all of you? The derivation of the order statistics and its distribution. Can you follow? Let me ask the name Vaishnavi Malwade. Do you follow what I am writing?
Yes, sir.
Okay. So next I proceed to introducing the concept of sampling. Okay. Let us talk about these concepts. Random sampling, population, statistic, sample, etc. So these are some commonly used terminologies. So why do we study statistics? Because we study observations. We study observations on say food grain production. We study observations on incomes. We study observations on industrial production. We study observations on financial markets. We study observations on petrol prices. We study observations on diseases. So disease data. So how many people get infected, how many people get cured, how many people die, how many people get treatment of a certain kind. We consider sports data. So we have observations on games, we have observations on plays, we have on the observations on players' performances, and so on. So a statistical population is nothing but a collection of observations. It could be quantitative observations or it could be qualitative observations. For example, I have mentioned these marks, performance. So these are all quantitative, but you can have qualitative also. For example, if you are considering say beauty of a person, so you can say good, bad, or ugly, isn't it? If you are considering something to be whether this is good or not good, so good or not good, you can have categorization into one or more categories. Okay, so then you can have a qualitative data. So a statistical population is a collection of qualitative or quantitative observations or measurements, you can say. So by a population in statistics, we do not mean the human population or the cattle population, etc. Population means certain measurements or observations. So a statistician is interested to draw certain inferences for that population. So for example, how many people would like to vote for a particular political party? So surveys are conducted which are called opinion polls. Okay, so say the surveyor, he will ask different people that which party you would vote for in this particular election. So then you are getting a qualitative data. That means they are telling they will vote for party A or party B or party C and so on, and then the data is summarized and certain results are presented, and their results are of various types. Like you can say that whether the voting percentage has increased or it has decreased, whether the preferences have changed or they have not changed. So there are so many types of studies that are possible. So for example, if you have an economic data, then you are looking at, say, for example, the family expenditure over a period of time, say monthly expenditure or an yearly expenditure, and so you are looking at that in a country like India or in a particular state, say Madhya Pradesh, or in a state like Maharashtra, or in a city like Bombay. What has been the change in the pattern of expenditure by the families, say in the last 1 year due to the effect of COVID? So then we will be looking at those data sets. So a statistician is always interested to collect the data on a population and then draw certain inferences from there. So in order to do that, he needs the help of samples, because it is not possible to look at the complete data every time. So for example, I talked about opinion poll. So you cannot ask each and every voter in the constituency that to which party he will vote for. So because that is done anyway by the polling. That means when the exact polling is done, then that data will come. But before that, the statistician can collect the samples, and from there he will like to predict. Okay, so sometimes the prediction may be correct, sometimes the prediction may be wrong. If we are collecting the data on the effect of, say, vaccine on the people, then it is not possible to collect the data on each person on which the vaccine has been administered. But we look at the sample of the people, and then we look at what is the effect. So based on that, certain predictions are coming. Like you have seen that they say Covaxin is 81% effective, the Oxford AstraZeneca is 95% effective, and so on. So different kind of data are coming, and that is based on the samples only. It is not based on the actual full population. So that means a statistician is interested in a sample. So a sample is nothing but a subset of the population. Sample is a subset of population. Now, what kind of sample you would like to take? You would like to take that sample such that it is representative of the whole population. For example, if you are doing a survey on incomes, say per capita income of the people, and you select the people only from a particular strata of the society, then it will give you a biased result. For example, you choose only billionaires or millionaires, then you will feel that the country is very rich, whereas it may not be. Similarly, if you collect the data only from a zone where you have only staff who are working in a low paid jobs, then you will get very low income. So your sample should be such that it is representative of the population. So for that, the statisticians devised a method called random sampling. That means you should choose the sample in such a way that each unit of the population has the same probability of getting selected into the sample. So random sampling, here each unit of the population has the same probability of getting selected into the sample. So that is why you will read the terminology in the books. It is written let x1, x2, xn be a random sample. So it means that it has been selected in such a way that each unit of the population has been represented. So that means they had the equal chance of getting selected into the. Another thing which helps this thing here is that if you have a random sample, then the observations are considered to be independent and identically distributed. Therefore, you can derive the joint distribution of the sample, and then we will like to use the certain functions of those random sample. For example, I may like to use the sample mean, I may like to use the variance of the sample, I may like to use the maximum of the sample, we may like to use the median of the sample. So then we will be able to derive the distributions of those quantities. In fact, I have already given you certain examples here. For example, if you have a random sample from Poisson distribution, then the distribution of the sum, that is again Poisson, that we have derived using the moment generating function approach. If you are having a random sample from an exponential population, then the distribution of the sample mean, that is a gamma distribution, we derived it using the MGF approach. Similarly, when the distribution random sample has been taken from a normal distribution, then the distribution of the sample mean is again normal with mean same and variance divided by n. So these are the results which we derived. So these results are called, that means we are deriving distributions of the functions of the sample observation. So that has a name in statistics. So let me now talk about that. So let x1, x2, xn be a random sample from a population suppose PDF is small fx, okay. So PDF or PMF, okay. Then the joint PMF or PDF of x1, x2, xn is given by product of okay, and you can derive the distribution of other quantities by using this one. So a function t, that is t of x1, x2, xn, is called a statistic. For example, x bar, that is 1 by n sigma xi. You can have xm, that is the median of x1, x2, xn. xn, that is the maximum of x1, x2, xn. You can have the minimum. So these are all examples of statistics. Okay, you can have s square. This notation I am defining now: 1 by n minus 1 sigma xi minus x bar square, I is equal to 1 to n. Okay. This is also called actually the sample variance. This is sample mean. This is sample median, etc. So sample maximum, sample minimum. The probability distribution of a statistic is termed as a sampling distribution. Okay. So one of the first results that is obtained using the distribution of sample functions, that is related to the distribution of the sample mean. Okay. So it is called asymptotic distribution. So asymptotic distribution means as n tends to infinity of the sample mean. This is one of the very powerful results in statistics. It is called the central limit theorem. Earlier I have told you that distribution of the binomial and Poisson converges to normal distribution. Now I will specify it in a general framework that distribution of any of the sample mean from any distribution also converges to normal distribution. So let x1, x2 and so on be a sequence of independent and identically distributed random variables with a mean mu and variance sigma square. Let us use the notation yn is equal to 1 by n, or yn let me not use because earlier we used yn for the largest order statistic. So let me put xn bar. Xn bar is sigma xi, I is equal to 1 to n. Okay. If you don't want this n, then if the inference is clear, because it is nothing but the mean of n observations. Okay. So I wanted to put n just to denote that thing. Then the limiting distribution of x bar minus mu by sigma by root n, that is root n, I will put it in the numerator, is normal 0, 1 as n tends to infinity. So look at the importance of this result here. I said that they are from any distribution but mean mu and variance sigma square. Then if I am looking at the distribution of the sample mean, so after standardization, that means by subtracting the mean and dividing by the standard deviation, it is normal 0, 1 for n large. Now of course you may question that what is the meaning of n large, but it has been observed that it has been observed in practice that n greater than or equal to 30 is large. So more than or equal to 30 observation itself actually gives you. For example, I gave you one exercise in the last class. If u and v are independent uniform 0, 1, then what is the distribution of u plus v? So it turned out to be triangular distribution. So immediately the shape is approaching normal. I can give you an exercise that you try for 3. If u, v and w are independent uniform 0, 1, then what is the distribution of u plus v plus w? You will find out that it is closer to normal. The shape becomes even closer. So for nice distributions, the convergence is faster, and for some of the distributions, the convergence is slower. but in general, the distribution of the sample mean converges to the normal for n greater than or equal to 30. Of course, in place of mean, you can consider the sum also, like you have done in the binomial and Poisson case. So if I consider Sn is equal to sigma xi I is equal to 1 to n, then the modified form of the theorem is like Sn minus n mu divided by sigma root n, then this also converges to normal 0, 1 as n tends to infinity. Well, we are not having the proof here in the syllabus, but I'll give you some examples and applications in the next class here. Okay. So I will stop today's class at this point. You can see that I have put several assignments and their solutions. Assignment number 4, 5, and 6. They are respectively, first one is on again continuous distributions, then fifth one is on function of random variable, then sixth one is on the joint distribution, and their solutions are also there. Today I will put one more on the transformations, the one which we covered today. So these are the topics which are to be covered in the next class test, which is to be held on the 6th. So you please solve these problems which are given there. Okay. So it's okay, fine. I'll stop today's class.